Alright, welcome to the first pre-lab video of the semester for the Chem 1211 sequence here in the Dahlonega campus in North Georgia. These pre-lab videos are going to be coming out for every actual experiment we do over the course of the semester, just to try and help you guys get a little bit better feel for what you're going to be doing, as well as highlighting a lot of the really important kind of conceptual topics, as well as kind of the actual procedural aspects of all the experiments that people really need to be aware of before they come to lab. And hopefully they will help you do better on both pre-lab quizzes as well as the pre-lab assignments that you're supposed to be completing before attending lab, as well as just make you a lot more comfortable during the experiment itself to hopefully just kind of keep the labs running a little bit smoother. So this week's lab, what we're going to be focusing on is the density of a solid. And so a few things about density, just kind of starting off. Part of the reason we're looking at density in particular here initially is that when we're in the chemistry lab, one of the most common things that we're going to be doing at kind of any level of chemistry, starting all the way here from general chemistry all the way up through like upper level, undergraduate classes, all the way up to like if you're actually in the workforce working in a chemical lab, you're always going to be what's called characterizing substances or compounds. And so what that term really means or is trying to look at is if you're trying to characterize something, you're trying to figure out what it is. And so if you're trying to identify a particular material or substance, we usually do that by looking at a host of kind of different chemical or physical properties. And density is actually one of those common physical properties that we can look at for a lot of solids in particular. And so we'll often see density as kind of a quick initial way to try and differentiate between different metals and the identity of different metals. In fact, if we think back to kind of like ancient times, density was one of kind of the quick ways that people were able to try and figure out if a particular solid was gold or if it was something else that just kind of visually looked like gold. Because visually they might look very similar, and so it's hard to tell, like, is this gold, is this something else? But the density is actually something that for actual, real, true gold is going to be very different than for pyrite or fool's gold or other things that might look like they're golden in color. And so density is kind of a nice physical tool, and like I said, it's one of the first ones that was used just from kind of a scientific perspective to begin with, and it's a nice easy one here, I think, to start off with in the semester for looking at kind of characterizing or identifying compounds. So when we talk about density, we do want to know what it is and how it's calculated in particular. So density, if you haven't seen it yet in lecture, is really just defined as the mass of a substance divided by the volume of that substance. And so when we go and actually calculate this density, one thing we do want to kind of pay attention to is going to be actually the units for this. So you've probably talked about SI units in most of your lectures, or if you haven't already, you'll be seeing it probably very shortly. And one of the weird things maybe about density is that mass normally has a standard SI unit of the kilogram, but really for density, we're typically going to see mass in units of grams instead, just because it's more convenient to measure. A kilogram of something is actually a fairly large amount of it, so grams are much easier to work with in a laboratory setting. And likewise for volume, standard SI unit for volume is the cubic meter, which is a huge volume actually. So we're going to work with something a little bit more convenient, like smaller volumes, and we're typically going to see the units for volume given in either cubic centimeters or milliliters for that volume unit. And those two values, again, if you haven't heard of them or seen them yet in lecture, 1 cubic centimeter is equal to 1 milliliter. So those units there, grams per cubic centimeter or grams per milliliter, those units are equal to each other. So they are identical and they are used pretty interchangeably, just depending on kind of what source you look up to look up the density of something. Now, every now and then you might see some of these other units like kilograms per liter or kilograms per meter cube. But for the most part, if you're calculating density, especially for this course, lecture or lab for 1211, you're likely going to be calculating always in units of grams per cubic centimeter or grams per milliliter. The pre-lab, as well as maybe one of the post-lab questions, does look at some different unit conversions for density. That's not so much necessarily looking at applications of how you're going to see density somewhere else. It's really more just kind of trying to help familiarize people with the idea of dimensional analysis, because you will see density used in dimensional analysis from time to time kind of going forward this semester, and it's usually a nice kind of convenient way for if you have a mass of an object but you need the volume of it because it's actually a liquid, then you can actually figure out, well, if I have a particular mass, I can figure out the volume if I know the density, or kind of vice versa. If you know the volume of something, you can find the mass of it as well, which is probably the more helpful thing that we'll be doing in a few chapters in the lecture when you guys start talking more about stoichiometry, and particularly solution stoichiometry. Density can have some applications there. Now, in terms of our experiment of what we'll actually physically be doing in the lab, if our goal is to calculate density, we basically need to be able to measure both the mass and the volume. So we're going to start by talking about the easier of those two things to typically measure, which is just going to be the mass. And there shouldn't really be anything kind of out of the ordinary here. We're just going to be using balances. All of the balances that we have set up in the lab, you can see kind of an image here of what most of them look like at this time. They should be able to measure to the nearest 0.001 grams or nearest milligram or thousandth of a gram, however you want to kind of think about it, for all of the masses that you measure over the course of the semester. So even if your measurement is like 0.020 grams, like keep that last zero, because every mass that you submit to CSE Pub is going to be expected to be to that third decimal place. And that's important from kind of a standpoint of looking at what's called significant figures or significant digits. So if you haven't talked about those yet in lecture, significant figures are really just a way of tracking how accurately we know things. And when we're doing calculations, we kind of pay attention to those significant digits, because if we only have an actual measurement with really maybe 3 numbers that we actually know, there's no way for us to then calculate, like say we measure a mass and there's only like 3 actual numbers involved in our mass. There's no way to calculate a density that's going to have, like 7 or 8 decimal places worth of numbers in terms of trying to know how accurately we found that density. So it's important for us to kind of have a reasonable expectation for when we're calculating values, like how well do we know them, and we figure that out using significant digits. Now, I'm not going to go over all the full significant figure rules here in the pre-lab video, because most of you are going to be seeing it in lecture, and the CSE Pub part of this lab isn't really going to test you on significant figures, although we will just kind of, like I said, introduce them from a measurement standpoint. From all of our mass this semester, like basically I said, the nearest milligram or nearest 0.001 grams, that's where all of our masses should be, because that's how accurate all of these balances are that we're going to be using. Now, in terms of actually using these balances, typically if you're going to actually find the mass of something, what we're going to be doing is having either empty aluminum pans or small plastic weigh boats, where basically you can add the actual aluminum pan or the weigh boat onto the actual inside of the balance here, so you might have to slide open the door to actually put it in there. And then what we'll do is once you have your pie pan, your aluminum pan, or your weigh boat actually on the balance, you're going to zero your measurement. So there's a 0 button here on all these balances. When you put the pie pan or weigh boat on there, it's probably not going to be exactly 0. We're going to tell it to 0. And then at that point, all we have to do is just add our sample to that aluminum pan or plastic weigh boat, and we can actually find the mass of our sample that way. So it's fairly straightforward, nothing too crazy out of that. But you do just want to make sure that you're zeroing it properly. Like, if you zero it while it's empty and then put your weigh boat on there and then add your sample, well, that weigh boat mass is now also part of your sample mass. So you do just want to be careful. And I think it's, like I said, fairly intuitive. If you do have questions, always ask. Like, you have an instructor and a TA always in the lab that can help you with that part too. Now, the volume part is a little bit trickier as far as how we determine volume for a solid or just substances in general. If the substance is a liquid, it's a little bit easier, but for solids, we have kind of 2 options. One of the ways we're going to do it here in the lab is actually by measuring this, the size of a sphere for one of our solid samples. And we're going to basically just measure the diameter of the sphere. And we're going to use something called the vernier calipers that'll kind of show and demonstrate how we're going to be using them in just a moment. And the other way is actually by looking at a change in water volume. And so we're going to do both of these in the actual lab. But we're going to focus here in this first. I'm just going to go through and show what's called these vernier calipers and actually kind of explain how to use them. So you'll see that this is an example of the vernier calipers everyone will be having to use in lab. And this top part and kind of bottom piece right here that I'm kind of bouncing back and forth to with the mouse, that part slides on these calipers. And you're basically just going to take kind of your pincher portion here of the calipers, and you're just going to kind of basically get a nice, firm, tight grip on whatever it is you're trying to measure. And then what you're going to do is actually read the calipers. And so I'm going to go over how we actually use kind of the different kind of tick marks here to go through and actually get a measurement of what is the diameter or what is the length that we're actually trying to measure. Because really these calipers are used to measure lengths, and they are very accurate. You'll see all of the little individual tick marks here are actually 1 millimeter. So the fact that we're actually, and as we kind of go through and make our measurement, we're going to see we can get this to basically the nearest decimal place of a millimeter, which is a really tiny length. So these things are actually quite precise for actually measuring these lengths that we can then use to find a volume. So this is kind of a zoomed in image of how that I'm going to use to try and explain how we use these calipers to make a measurement. So the first thing we're going to look for is actually going to be this 0 mark up here at the top, on the top row. This 0 mark is basically going to tell us where along this scale we're going to have everything that's going to come before our decimal place for our measurement in millimeters. Because again, all these tick marks are in units of millimeters. So this 0 right here, as we look at it, looks like it's between 25 and 26 millimeters. So that means we're like 25 point something millimeters. Now, to figure out what that decimal place is going to be, that's what this kind of inside part is down here in the bottom. And how this works, it's probably, if you've never used a vernier scale of any kind, probably looks a little bit strange. But how this is going to work is you're basically going to look at all of these tick marks here ranging from 0 all the way to 1. And you're going to look which of these tick marks exactly lines up with the tick marks on the scale above. And so like we look here at the 0, the 1, the 2, the 3, none of them are really lined up all that well. But it looks like the 4 is kind of spot on, right? And the 5 is very close, maybe just a tiny bit off. And then like again, like the 6, 7, 8, 9, 10, none of those are lined up very well. So what this is then basically telling us is that our decimal place for our measurement here is either going to be like a 0.4 or a 0.5. Can't really fault you necessarily for picking either one. It's very close. I'd probably say 0.4, but again, it's very close on either one of those. And this kind of gets us to this whole idea of how accurate our measurements are with things like significant digits. If we were actually going to record this then measurement to use for our lab, we would say this is 25.4 millimeters. And again, that very last measurement or last decimal of a measurement is always going to have a little bit of uncertainty in it because it's kind of an estimation. And so that's why I say like whether you put a 4 or a 5 there, it doesn't really matter all that much because that last decimal place always is the one that's going to, if there's going to be any error, that's the one that's going to be a little bit different. So there's always kind of a little bit of leeway on that last decimal place. But it is important when you go to CSE Pub to kind of input your data for the lab. One of the things you probably do want to be aware of is I think it asks for those units of this diameter to be in centimeters because your volume eventually is going to be in grams per cubic centimeters for its final units. But this, remember, is measuring in millimeters. So you will have to do a conversion of the millimeters that you get from your calipers to centimeters that you're then going to put onto CSE Pub and use for your calculations later. And basically what you're going to end up doing is once you've measured this diameter of your spherical balls that you're going to be looking at, you can use then that diameter to go ahead and find the volume of that sphere, right? If it's a sphere, then we can use just the volume of the sphere equation, 4/3 pi r cubed, to go through and actually estimate what the volume of that substance is that we're looking at. All right. Now, the other way we're going to go about trying to look at volume, and this is the way we'll do it much more often throughout the semester, and it's going to be using graduated cylinders. So how we're going to go about using graduated cylinders, kind of some general things to be aware of. Usually graduated cylinders are going to involve measuring liquids, and so we're almost always going to be using water or some sort of solution that is mostly water. So here, if we're looking at our image here on the right-hand side of our screen, all of our liquids, when they're in graduated cylinders, that are typically our water-based liquids, are going to have this kind of slight U shape to them, which we refer to as a meniscus. And so we always want to measure the volume at the bottom of that U shape or the bottom of that meniscus when we're making our volume measurements. And so it looks like right here, this is kind of like the bottom of our meniscus. That's approximately where we want to basically measure, or what we want to kind of figure out what is that numerical value. So kind of similar to how we were looking at the lengths a second ago in terms of like how many decimal places and things like that we want to give. When using graduated cylinders, in terms of the number of decimal places we want to be showing, we always want to give kind of one decimal place further than whatever the tick marks of the graduated cylinder itself represent. So this graduated cylinder here, we see basically tick marks, we're like 1, 2, 3, 4, 5 are kind of the large tick marks, but there's 10 little tick marks kind of between each of the larger numbers that we see there. So each of these little ones, this would be like if we were at this line right here, this would be like 5.1 milliliters, and these are all of our graduate cylinders do measure milliliters for their volume. In our case, if we're looking at where the bottom of this meniscus is, it kind of looks like if we're starting this large line here was 5, so this would be 5.1, 5.2, 5.3, 5.4 is here, but that's above the bottom of our meniscus. So we know that our volume is somewhere between kind of 5.3 and 5.4 milliliters. And again, that last decimal place that we're going to give for this measurement is just going to be an estimation. And so if you think it's exactly halfway between the 3 and the 4 tick mark, or the 5.3 and 5.4 tick marks, you could say it's 5.35 milliliters for your volume measurement. Looking at this just kind of with my own eyes, I'd say maybe somewhere like 5.37 or so. But again, that last decimal place, if you looked at this and read this to be about 5.40 or even like 5.38 or 5.39 or 5.35, like none of those would really be wrong, right? That last decimal is up to kind of your interpretation of exactly where you think it is. And again, that's why we kind of have significant figures that we'll be talking about all semester long that we use in calculations, because that takes into account kind of the accuracy of our measurement of how well we know things, and the fact that the last decimal of all of our measurements is always going to have that little bit of kind of leeway or kind of estimation involved in the process of getting it. Now, what we're going to be doing with the data that we actually collect in the lab, and just to talk a little bit about kind of procedurally, when you're looking at measuring the mass of your different substances, I think that the general directions of the experiment are going to have you do basically samples A through E and get a mass of each of them. And it's also for using the graduated cylinders, like what we had here in this image. You actually see kind of some spherical metal balls here that we're measuring the volume of. The way we're actually going to measure volume for samples A through E, which, by the way, for the mass part A through E and the volume part A through E, those samples should be the same, so don't change anything about them when you're going from kind of one to the other after you've gotten mass, and then you go to measure the volume of each of those samples. What you're going to do to find the actual volume is you're going to add a little bit of water to your graduated cylinder. And so if you have just water in here, your volume, let's say your volume is exactly 4.0 milliliters or 4.00 milliliters. You're then going to add your metal spheres or just your solid that you want to know the volume of, and you're going to see what's the new volume now of the water, like how high has it risen. And what you do is you take the change in the volume, because the change in the water volume in the graduated cylinder after you've added your solid to it should just be the volume of the solid itself. So let's say our initial volume of water was at this 4.00 mark. We added these 4 spheres, and now it's up to 5.37 milliliters. Well, we take the difference of those two, so 5.37 minus 4.00, that means the volume of these 4 spheres would be approximately 1.37 milliliters. And that would be the volume we could then use to find our density, or we're actually going to use then to make a plot to find our density. So for that plot then, you should, at the end of the actual experiment, and this part about plotting things, this is going to be done outside of lab. It doesn't have to be done before you leave. But if you have like a laptop or something with you and you want to just kind of plug these things into Excel quick, it only takes a few seconds to kind of look and see if you can get a plot that makes sense. But you're basically going to have 5 measured masses and 5 measured volumes that correspond to those masses. And what we're going to do is we're going to use kind of that whole collection of data to make a plot in an attempt to kind of just reduce the error of our density calculation. Because if all we did was take one sample and we just measured the mass once and the volume once, there's still a decent potential that there can be error in either our mass or volume measurement. And by making a whole bunch of kind of sets of measurements, having more data points should basically help eliminate any potential error. If one of those mass measurements or one of those volume measurements was a little bit off, the fact that we have a bunch of other ones kind of in tandem that we're all looking at one time helps reduce some of that error. Now, when you're making the plot for your data and you're actually going in to make your Excel plots that you'll be uploading to CSE Pub, axis orientation does matter for them. So keep in mind, even though for this particular case, there's not an easy like dependent or independent variable for you to recognize between mass and volume, but the thing that's important to us is we will eventually want to find density, right? So if we think about plotting all of our data points where basically if we know the mass and volume, like kind of keep them together as a pair for like an X and a Y value, well, if we eventually have all of these data points together, our goal is to make a linear regression line. So a line that's going to have some slope to it. And the slope of a line, if we're calculating, is always going to be the change in the y-axis over the change in the x, and density is mass over volume. So basically, this kind of looking at it from this perspective, we want mass on our y-axis and volume on our x-axis, because what we can do is then we take all of our data points for our masses and our volumes, and we make a plot with mass on the y-axis and volume on the x-axis. If we then make a linear regression line that hopefully either passes through or very close to all of the data points for our measurements, then the slope of that line just will be our density. And so that's how we're going to go about trying to calculate density for different solids here in lab. You will be making a couple plots to go through and calculate those densities. And again, the reason we're making these plots and using kind of the slope of these lines is that by taking multiple data points into account, it's hopefully minimizing the error of if we had like one bad measurement, that it's not going to mess up our density determination all that much. And to give a sample kind of what we expect these density plots to actually look like, so here's just kind of a quick example. We have mass plotted on our y-axis, volume on the x-axis. Notice our units, mass in grams, volume in milliliters here. And we have all of our different data points. So like we'd have like a sample like A, B, C, D, and E. So five samples, along with one additional data point that everyone should include in their plots, and that's the origin, like 0, 0. Because if something has 0 mass, it should also have 0 volume. We won't always include the origin in all of the plots that we make this semester, but we do include it in places where it makes sense. And so if something does have 0 mass, it should have 0 volume. So we will use 0, 0 as an additional kind of 6th data point in the plots that we make. And then our goal, like I said, is to make these linear regression lines or add these trend lines to our plots. And we're going to look at the slope. So you do want to display the equation of your linear regression line here. And so here we see this is the slope of our line, 5.483. That means the density for this particular substance would be 5.483 grams per milliliter, right? Because again, mass in grams, volume in milliliters for our units there. So that's kind of what you're working towards at the end of the lab from kind of a calculation sense and making these plots is really we just want that linear regression line because it's really going to help us figure out kind of almost an average density between everything that's standardized a little bit better rather than just having like actual densities of each individual data point and looking at how close each individual data point is because singular measurements do have a decent potential for error. Like for instance, if we're looking at our linear regression line, there's one data point that's not nearly as close as the others, but by having a lot of data points, it kind of helps correct for that. And so we can actually still get a very accurate density measurement, even if one mass or one volume measurement was a little bit off. All right, so as kind of a wrap up here, some final takeaway points that I'd like people to have as you kind of finish the experiment and kind of finish the calculations for this lab. The idea that we want to be able to characterize compounds and materials. This is something that for those of you going on to take more chemistry courses or potentially even physics courses as well, identifying kind of what a compound or a material is or what you've made from a chemical reaction, for instance, is a really important part of kind of just the scientific process. You can't always just assume what it is that you have. You want to be able to prove you know what something is. Density is one of the ways we can do that for some solids. And so that's why we're looking at density kind of here today. And then in terms of just density itself, everyone should be a little bit more familiar with what density is and how it's calculated, and also specifically just the unit part. Units are probably the thing that people tend to mess up the most when doing density problems or density calculations. And so just be aware, like grams per cubic centimeter or grams per milliliter, those are our common units we're typically going to see. And so those are the units you always want to have expressed typically when you're calculating your densities. And then hopefully, just getting a little bit more comfortable plotting data. We're going to be doing this pretty frequently throughout the semester, having to make plots like this and look at linear regression lines and use their slope to help figure out information. And so we want to start kind of getting the habit of when we have to make a plot, understanding like what goes on which axis for the plots as we make them and how that affects like what the slope of our linear regression lines actually tells us. So we always want to make sure we're getting kind of things in the right axes. So in our case, since we want the slope to just equal our density to make our lives a little bit easier, we want to make sure that mass goes on that y-axis, and then we get the volume on that x-axis for our plot so that the slopes will give us our densities directly. And the last thing here, just getting introduced to kind of some common measuring tools from the lab. You saw we use vernier calipers, which we won't use too much throughout the semester, but graduated cylinders for measuring volume, balances for measuring mass, we're going to be using those almost every week, kind of going through making measurements of things. A lot of the labs we do involve solutions that we need volumes for things for, so using graduated cylinders is going to be very common. And so one of the things we want to keep in mind, we saw earlier, like in terms of the number of decimal places to give for those volumes, that's something we always kind of want to have in mind as we make those measurements throughout the semester. Likewise for mass, kind of general procedures as far as kind of zeroing things properly, making sure everything's always to that third decimal place for grams, and just kind of having that with, because now it's kind of just an easy tool that we're used to using because it is something we'll use frequently throughout the rest of the year. All right, I think that wraps up what we have for our density lab as far as kind of general things we want people to know and be aware of before coming to lab and doing your experiments this week. Hopefully everyone has a good week, and we'll see you with the next video.